Hi, Chem 240. This is Dr. Ricardo. Sorry about that. We are doing the fourth video of the kinetics chapter, which is chapter 14. We left off on page 17 of the notes. The last thing we talked about was the Arrhenius equation. What the Arrhenius equation gives you is the relationship between the rate constant, the Kelvin temperature, and the energy of activation. So a very typical calculation that someone would do is to measure the rate constant for a particular chemical reaction at two different temperatures. T1 would give you K1, T2 would give you K2. Doesn't matter which is bigger, just be consistent. Make sure the ones go with the ones and the twos go with the twos. If you mix them up, obviously, you're going to get junk. Okay? In every single case, as the Kelvin temperature goes up, the rate constant increases. Okay, so K2 will always be higher than K1 when T2 is higher than T1. Okay, now if you measure the rate constant, you go in the lab and you actually measure the rate of the chemical reaction and then calculate the rate constant for that particular temperature, then do the same exact experiment with the same concentrations at a higher temperature, measure the rate for that reaction, then go back and calculate the K, you'll have two Ks at two Ts. Well, what can you dig out of that? You can solve for the energy of activation, which is the difference between, talked about this a little bit last time, right? The difference between the starting point of the chemical reaction and the barrier that you have to get over in order for the molecules to react, okay? So this is on the scale of enthalpy. This we learned about in Chem 1 is the difference between the starting point and the final point. That's called delta H. That's the energetics of the reaction. That's how much heat is either lost or gained. But there's always some barrier because you have to break old bonds and form new bonds that you must get over. Okay? Well, if your particular chemical reaction is conducted under at higher temperature, the rate constant is going to be higher because there's a larger percentage of the molecules that have enough kinetic energy to overcome this barrier, right? So you're increasing the percentage of molecules that can make it up over this hill. How much energy does that take? Molecules would have to hit with 60 joules per mole of energy. So if you can give the average molecule in the beaker 60 joules per mole, then 50% of them will have enough energy to go on to reaction. The reaction will happen very quickly. So this was the kind of diagram that we looked at where we were looking at the fraction of the molecules with enough energy, the fraction of the molecules with a certain energy. So at a low versus the kinetic energy, okay? Okay, or this down here would be energy, okay? All right, so here's our barrier. This represents, EA represents 60 joules per mole, okay? 60 joules per mole. That's how much energy, that's a fixed number, that's how much energy the molecules have to have when they hit so that their kinetic energy can be translated into a fruitful reaction. Well, if you're at a very low temperature and the average kinetic energy of the molecules is only something like 30 down here, almost none of the molecules have enough energy to relax, so to react. So here's the bell-shaped curve, right? Tails off down here, and only this little tiny bit, this little area under the curve, maybe 1% of the molecules that hit each other have enough energy to react. When you increase the temperature, you dramatically increase the average kinetic energy of the molecules. So here's the average kinetic energy. It's the top of this mountain. So at the higher temperature, right? Let's make that higher temperature the average kinetic energy of the molecules be something like 55 kilojoules per mole. Okay, well look at that. At 55 kilojoules per mole, right, they're so close to the kinetic energy needed in order for the reaction to occur that the bell-shaped curve broadens and moves to the right. So what happens in that case? Oh my goodness, look how many molecules. All of these guys in the hatched lines, all of these guys have enough kinetic energy to react. It's the area under this bell-shaped curve. So that portion, to me, looks to be about 40% of the whole thing. There's the whole thing. Okay? All right, go to an even higher temperature. Go to a ridiculously high temperature of 500 Kelvin, where maybe this guy's average kinetic energy is 100 kilojoules per mole. Remember, kinetic energy is directly proportional to temperature. So as you increase the Kelvin temperature, you increase the kinetic energy. Well, what happens to our curve? This same curve now has slid or moved all the way over here to the right. Now, the average kinetic energy is something like this, right? You needed 60 to react. Maybe we have 100, right? Well, look at it. Everything in the yellow, all of that area under the curve, that fraction of the molecules, what does that look like compared to the whole curve? That yellow part versus this little slice over here. Well, that to me looks like maybe something like 90 or 92%. So 92% of the molecules, when they collide, have enough energy to react. So the reaction is going to go so much faster at higher temperature. So that's what you're doing, okay? What you're doing is, in the Arrhenius equation, you're calculating the relationship between rate constant and temperature. Why does the rate constant increase so dramatically? Because you're giving a larger fraction of the molecules enough kinetic energy to overcome the energy of activation. Couple of points about this. All temperatures have to be in Kelvin. Whenever you use R, you use the energy R, 8.31 joules per mole Kelvin. This has no negative sign on it. This guy should come out to be positive when T2 is bigger than T1, right? And what do you expect over here? The rate constants you're going to put in, and you put, doesn't matter what units you have. If it's a first order rate constant, it'll just be 1 over seconds. If it's second order, it'll be 1 over molarity times 1 over seconds, but they'll be consistent. The top one and the bottom one will have the same units all the time because they have the same chemistry, right? So they'll cancel out. You just take the natural log of that side. Okay, so practice this at multiple temperatures. All right, the next thing that we're going to discuss is reaction mechanisms. Okay, so what is the definition of the reaction mechanism? Well, the reaction mechanism is the steps in the overall chemical reaction. Okay, so let's put an S on that. It's the steps in the overall chemical reaction. All right, so here's an example. If you know that you put together nitrogen dioxide and carbon monoxide, they react to make nitrogen monoxide and carbon dioxide. So they're basically just exchanging oxygen. So one oxygen is being transferred from here to here. So this is the overall reaction. So if we didn't know anything about the mechanism, the only way we could figure out the kinetics of this is to say, okay, if this is the overall reaction, we could always write the rate law, right? And the rate law would be the rate for this chemical reaction would be the concentration of any of the reactants in moles per liter times two exponents that we need to figure out. So we would have to experimentally figure out what X and Y is. Okay? Well, if it turns out that you know what the mechanism is, you know how the particular chemical species actually hit in the beaker and go on to form the product, and it's not just the overall reaction that you're looking at, then there'll be another way to get X and Y. Okay, right now, how do we get X and Y? We do a series of experiments where we change the concentration of nitrogen dioxide while keeping the concentration of carbon monoxide the same, see what happens to the rate. Then we do another couple of experiments where we change the carbon monoxide, keep the nitrogen dioxide constant, and see what happens, and we dig out X and Y. So we practiced that already, and it's a big part of the exam. Okay? If you're given the overall reaction, overall mechanism of the reaction, how the particles actually hit into one another, then there's another way to do it. So let's take a look at this mechanism, and then I will show you how to do it. It's very simple. All right, so we have learned from a kineticist has told us that they studied this reaction and they've determined that the way nitrogen dioxide reacts with carbon monoxide is in a two-step process. So every time you go through one of these reactions, two steps had to occur first. The first step is that the nitrogen dioxide, which is one of the reactants, actually smashes into another nitrogen dioxide and makes NO3 and NO. So that is a direct chemical reaction, right? This is happening in the beaker. This never happens in the beaker. NO2, whenever it crashes into CO, those don't go on to make fruitful reactions, right? You need nitrogen dioxide to hit another nitrogen dioxide, okay, in the gas phase. This is in the atmosphere pretty much, okay, to make NO3 and NO. So that's the first step of the reaction. Even though it looks as though you're just handing an oxygen from here to here, that's not the way it occurs. So you have to dig down further and experiment. What is the actual mechanism that occurs? Well, this is what happens in solution. These are actual molecular reactions. This is just the overall reaction that you see. All right, then that NO3 is very short-lived. It's the chemical species that hits the carbon monoxide, delivers the carbon monoxide to it, delivers the oxygen to the carbon monoxide to make the product CO2, and kick back an NO2. But this NO2 is the same one of the NO2s that you originally had. So we have two interesting things going on here. One is we create something called a chemical intermediate. An intermediate is something that you form, but then later quickly use up. So you make it and then you use it. So if I was to sum up these two chemical reactions, I would create an NO3 and then I would use up an NO3. So these would cancel out. So for chemical reactions, you can add them up just like you would add up mathematical equations. So what happens to this NO3 and this NO3? There's one of them on the right, there's one of them on the left, they would cancel out. Okay? So something that you create and then gets used up is called an intermediate. Okay? There's also something called a catalyst. A catalyst is something that you use and then you subsequently get it back. So this is self-catalyzed. The molecule that you need in order for this reaction to occur faster is actually one of the things that's in the reactant. So it's self-catalyzed. Pretend this is NO2 is the one that eventually goes on to become the product, NO, okay? Well, there's another one that you need just for a short period of time. You use it up in the first step, but then you get it back. So that's a catalyst. Something that you use up and then gets back. So see how catalysts will cancel out this way, one on the left, one on the right. Intermediates will cancel out this way, one on the right, one on the left. So it's the order in which they happen. So that makes sense. Intermediate, you form for a little while and then use up. Catalyst, you use it and then get it back. So see how this one and this one cancels out and this one and this one cancels out. So what's left? The first NO2, okay? This guy canceled out, so this CO is left down here. I don't have to write the NO3 because it canceled out with that. What's left on the other side? This guy canceled over here, right? This one and this one cancel out. Oh, sorry. No, this is one of the products. So I'm sorry. This guy's a product, so this guy and this guy cancel out. So here's one product, CO2. That's definitely a product. And then here's the other product, NO. So those two things don't cancel out. This one and this one don't cancel out. Look at it yourself. And this one and this one don't cancel out. This is CO. So these two and these two are the things that don't cancel out. This cancels with this cancels with this. Okay. So you can always rewrite. If you have the steps in the mechanism, you can put them together to get back the overall equation. That has to happen. You have to be able to rewrite the overall equation from the series of steps. Well, that kind of makes sense, right? All the steps in the mechanism must add up to the overall reaction. Each step is called an elementary reaction. So this is the first elementary reaction, the first step. The second step is the second elementary reaction. Elementary reaction means actually the way the particles are smashing into one another. Here's that definition. Elementary reaction is a single molecular event, such as a collision of molecules resulting in a reaction. The set of elementary reactions whose overall effect is given by the net chemical equation is called the reaction mechanism. So this is the mechanism, the steps that give you back the overall reaction. It's got to happen somehow, right? You don't know the exact steps, okay? So if I told you that the net result was that you went grocery shopping and you came back with a bunch of groceries. Well, there's a series of steps that led you to go grocery shopping. First, you got in the car and drove to the grocery store. That's step one. Step two, you shopped. Step three, you drove back. Step four, you took everything out of the car and put it in the house. That's the series of steps, okay? The series of steps will always add back to the overall, which is went grocery shopping. So you can see the difference. Okay, now this is really what's new, okay? The rate law for any elementary reaction is given below. All you have to do when you know it's an elementary reaction, not an overall reaction. For an overall reaction, you have to go back and do the series of experiments to figure out how they reacted. You've got to go back and figure out what X and Y is. That's if you don't know the mechanism. If you do know the mechanism, the coefficients from the balanced chemical equation in an elementary step are the exponents. Okay, so I know that's a little bit confusing. I told you before, don't just make the coefficient the exponent, but if it's an elementary step, it's actually one of the steps in the mechanism, then you don't have to do a set of experiments. The actual coefficients, how the molecules hit into one another, are the exponents. Okay, so let's take a look at that. I'm telling you that for our chemical reaction here, here's an elementary step. A plus hits into 2B. This is a TER reaction. 3 things have to hit at the same time, which is rare, but it's the one we have written here. And they go on to make products, right? Kinetics is all about the reactants, right? You don't spend much time thinking about the products. You watch the reactants react. So the rate for step 1, right? This is step I. The rate for step I is equal to the rate constant for step I times the concentration of A to the first power, because its coefficient is 1, times the concentration of B squared. Okay, only if it's an elementary reaction can you do this simplification of just taking the coefficients and making them the exponents. If you have only the overall reaction, you need to go back and look at a table of data where you change the concentrations and you figure out what X and Y are by inspection. Okay? So the coefficients become the powers in an elementary reaction. Okay, we talked about in our last example back here, one of these guys was an intermediate and one of them was a catalyst. Let's show you the definition for that. A reaction intermediate is a species produced during the reaction that does not appear in the net equation because it reacts in a subsequent step in the mechanism. You create it and then you use it up. You create it and then you use it up. So you never see it. Intermediates are formed and then used up. They often only have a fleeting existence, meaning they might last for just hundreds of a second or even millions of a second. A catalyst kind of the opposite. Catalyst or catalysis is the increase in the rate of a reaction as a result of the addition of a catalyst. There's going to be two different kinds. You can either have a homogeneous catalyst, which is in the same phase. So let's say you have everything dissolved in solution, and this reaction is going to be catalyzed by NaCl. You dissolve the NaCl in solution, and it would be in the same phase. A heterogeneous catalyst is in a different phase. So a typical example of this is maybe iron is a catalyst for a particular chemical reaction, and you take solid iron, you grind it up, and you put it at the bottom of the beaker, and the iron creates a place for the chemical reactions to occur. They happen on the surface of the iron. So the iron is needed to speed up the chemical reaction, but it's in a different phase than the chemical reaction. So that would be two phases. Another thing that you could actually have is you could have an oil-water mixture in a beaker. So here's your beaker. And oil usually floats on top of the water. Okay, you could put the catalyst, maybe the catalyst dissolves in the water, in the oil only. It's only soluble in the water. But here's where the chemical reaction is going to occur. Okay, so the chemical reaction is going to happen between A's and B's. So what happens is the A's and B's, when they just hit each other in solution, can't react. But if they meet up with one of the catalysts that's sitting at the phase boundary for a second, the A and the B can react at the surface there because X is kind of hanging out at the edge, and it can provide a place for the chemical reaction to occur. After they occur, they kick out the X, and you just get your AB bound together. So the catalyst happens at the interface between the two layers. So this would be heterogeneous catalysis because this catalyst is not dissolved in the oil. Okay, it's dissolved. The chemical reaction is happening in the aqueous phase, but the catalyst exists in the oily phase. Okay, and our other example was here's your beaker. Here's the chemistry is going to happen in the aqueous phase, but you put some iron beads down at the bottom, and the mixture from the liquid, A's and B's have to get together. They can't react up here because they need the iron to help them. They react at the surface of the iron, and they produce the new thing, C, but it happens in a heterogeneous way. Okay, so heterogeneous is in a different phase. Here it's happening on the solid instead of in solution. Here it's happening in the oil instead of solution. Regular catalysts happen in solution with all one phase. So this is aqueous, this is all water. And maybe this is acid catalyzed. So if I have some H pluses in there, they help the A's and B's get together to go on and make C, because maybe the hydrogen ions participate in the reaction, are used to help make C, and then they're kicked back out. So you use them and then you release them. Okay, but it's all happening in the same solution. I don't have solid and liquid or liquid and a different liquid. It's all happening in aqueous solution. So this is homogeneous catalysis. This is hetero. Okay. Okay, let's take a look at a proposed mechanism and let me work your way through it. Okay, so here's our reaction. Okay, so the catalyst goes into the chemical reaction. You need it for A and B to react, but then after A and B react, then they make a new bond. So A and B makes a new thing. We could call it C, but I just have it A bound to B. So this is supposed to be a bond in there, a single bond holding A, B together. Look, C is then released. So if I wrote the overall reaction for this, what happens in math? I have the same exact thing on the left and the right. They would cancel out. So here's our proposed mechanism. Okay, it's going to happen in 3 steps. Step I, step double I, step triple I. Okay. In step I, A reacts with the catalyst C. Okay, so because it's a catalyst, I put a box around it so you can keep track of it. To make AC, and A is bound to C now. So these two guys hook up and make AC. AC, though, turns around reacts with B to make A bound with B, bound with C, where A is in the middle. So it has two single bonds. So the new bond happens down here. Okay, so A first hooks up with C to make AC, and then AC reacts with B, the B attacks over here, and I get this cool little, looks like a three-part molecule. Okay, you can pretend they're elements, or you can have them be other molecules. But basically, I have one big molecule where the A part is in the middle. Well, guess what? A, B, C then, spontaneously, just because of heat energy or runs into the wall or runs into another molecule, decomposes, it breaks apart on its own, and it knocks C back out. Now I just have AB. Well, how cool is that? I needed C to get in there to create this first intermediate, AC. AC is created in the first step and then used up in the second step. What's that called? That's called an intermediate. So I circled the intermediates. Okay? C is used in the first step, but then kicked back out in the third step. What do we call that? That's a catalyst. When I need something, but then I get it all back out. So it's like it didn't even participate. I use it. It's like when you borrow $20 from somebody to go to the movies, but then you pay them back. Okay? Well, after a month, you forget that you even borrowed the $20 because you don't owe them. You already paid them back. But if they didn't give you the $20 up front, you would not be able to go to the movies. So this is kind of like borrowing money short term, right? You need the money to go, but then you give it back. Okay, so that is a catalyst. Now there's one other intermediate that I should have circled. Look at this guy. I create in step 2, A, B, C, but then I quickly use it up in step 3. So I should have circled this guy too. So I'm kind of circling the intermediates and putting boxes around the catalyst. Now, all intermediates, by definition, have to cancel out. I create them and then I use them up. So this one cancels with this one. This one cancels with that one. All catalysts also have to cancel out. I use them and then I get them back. So see how that cancels out this way, right? If you create it first and then use it up second, it's an intermediate. If you use it and then get it back, it's a catalyst. So the only thing left standing is things without boxes and circles around it. So I got A plus B plus C goes to AB. This is still standing, plus C. So in fact, I could have just left this guy out over here. Okay? So that's the way we ordinarily do it. So the way you can represent catalysts, you don't do this with intermediates, is you put a little C on top of the line. And what does that little C show? That you use something, but then you get it back. We don't really write the catalyst in the chemical equation. We're much more likely to do that. And a very typical chemical reaction is something that's acid catalyzed, like this one I drew here. I would say A plus B goes to making C, but not without acid around. Okay, so the pH of the solution would never change, but I would need the solution to be at a low pH where there's a high concentration of H plus in order for this reaction to happen quickly. Okay, so I use it, I need it, and then I get it back. That's a catalyst. You write it on top of the line like that. Okay, so there's 2 ways of writing the overall reaction. More typically, we're going to jump right to this second way. Okay, let's write the rate law then for those 3 steps. So what did I teach you in the last section? I said that if it's a molecular reaction, okay, if it's a step in a mechanism, okay, it's an elementary reaction, then just by looking at the rate law, just by looking at the mechanism, you can come up with the rate law. It's the concentration of all of the reactants to the coefficient that they have. So the rate for step I is equal to the rate constant for step I. I'll make this a little bigger. Okay, it's the rate constant for step I times the concentration of A to the first times the concentration of C to the first, right? Whenever we're doing kinetics, we're only interested in the concentration of the reactants. The concentration of the products does not make it speed up or slow down. It's already too late. You already created it. Okay? What's the second step? Well, the rate of how fast the second step takes place is equal to the rate constant for the second step multiplied by the concentration of any reactant to their coefficient. So AC, there it is, that intermediate's concentration is to the first power. Why? Because there's a 1 here. And B is to the first power, so it's first power here. Okay, so you get the idea. For step 3, or step III, it's the concentration of this intermediate to the first power. Okay, so the rate for step 3 is equal to the rate constant for step 3 times the concentration of that reactant to the first power. So if somebody asked you, what's the overall rate for the reaction? How fast does it occur? The overall rate is the sum of the rate for the first one, plus the rate for the second one, plus the rate for the third one. So you could add all of those terms up and get the overall chemical equation. Okay, molecularity is a term that's used to describe the number of molecules that participate in elementary steps. Let me read the definition and then we'll go through it. So molecularity is the number of molecules on the reactant side of an elementary reaction. So this first one, step I, has a molecularity of 2. It's bimolecular. It takes 2 molecules to smash into each other. Because remember, these are the actual way that everything is reacting with one another. Okay? Step 2 is also bimolecular. It takes 2 molecules to hit into one another. So it's also bimolecular. And step 3 is unimolecular. Unimolecular means there's only 1 molecule on the reactant side. This thing, that's a decomposition. This thing just breaks up. Okay? Termolecular reactions is if you actually had a 3-particle collision, which if you think about it, is very rare in physics and chemistry. How do 3 things hit each other at the same time? Usually, it's a chain reaction. 2 things hit into one another, and the third thing comes in a little bit later, right? How do you get the timing that 3 things hit at exactly the same time? Okay? Not too often, okay? Very, very rare. So what you're going to see is most elementary steps are going to be either bimolecular, 2 species. Remember, these could be elements or compounds, 2 things smashing into each other, or just 1 thing decomposing. Bimolecular is 2, unimolecular is 1, termolecular is 3. Okay, here's a cool thing that we're going to talk about is the rate law, the relationship between the rate law and the mechanism. Okay, so it's the relationship between rate law and mechanism. First thing is, let's talk about the rate determining step. There almost always is 1 step in the process that's much slower than the rest. So if you have a 3-step process or a 4-step process, usually the way nature works is there's 1 thing that's the log jam, the 1 thing that takes the longest amount of time. Okay, let's go back to our person going to the grocery store. If you live close to the grocery store and you're going to go get your groceries for the whole week, driving to the grocery store is 5 minutes, shopping at the grocery store is an hour, and driving back is 5 minutes. So which is the slow step? The actual shopping at the grocery store. That's the thing that takes the most time. It's not the transportation back, okay, and forth. So there's usually 1 step that's much slower than the rest. So we call that one the rate determining step. If you were describing to people, okay, how long it took you to go grocery shopping, you'd probably tell them an hour. You probably wouldn't even bother to mention that it took you 5 minutes to get to the grocery store and 5 minutes to get back. They said, well, how long were you shopping? I was shopping for an hour. Okay, so that's very, very typical that we're going to have one of the steps, one of the 3 or 4 steps in the mechanism is going to be the driver, the one that's going to determine how slowly the reaction occurs. The other are going to be so fast that they don't even matter. Okay, so that's what we're going to be looking for. That's the important step, the slowest step, the rate determining step. So here's an example. I'm going to give you the overall reaction. Then we're going to look at the mechanism. going to give you the mechanism. Now, in our class, it's very hard to figure out what the mechanisms are, so we're going to basically tell you what the mechanism is, and then you're going to go from there and do some work for us. Okay? So here's the overall reaction and the mechanism. Okay? So the question is, determine the rate law from a mechanism with an initial slow step. So the first step is slow, and then the other steps after that are very, very fast. So here's our example. The overall reaction we're going to study is ozone. This is again a gas phase reaction. Ozone in the atmosphere reacts with 2 units or 2 molecules of nitrogen dioxide to create oxygen and dinitrogen pentoxide. So this is a form of smog. Okay, so we're kind of making smog. Okay, now this is the overall chemical reaction. This is the net product that we wind up with. Okay, it may not be the case that these 3 things all hit each other at the same time and I get a termomolecular reaction. In fact, that's not the proposed mechanism. People, kineticists, which are the kind of chemists that study kinetics, okay, they studied this reaction because this is very important in air pollution, and they've determined from doing their experiments that the mechanism, and the mechanisms are always proposed, okay? This is kind of like trying to figure out if you have a murder scene, right? And you work your way back and propose what happened, okay? As to how the murder actually occurred based on the evidence that you see later. You're really just proposing that, right? If you're an investigator, you don't really know, you don't have a videotape to show you exactly what happened, but you're proposing what happened. So the proposed mechanism, and it'll stay that way in the textbooks, the proposed mechanism for a particular chemical reaction until somebody figures out that that proposed mechanism isn't correct, okay? So in a sense, all the mechanisms, some of them are well worked out and we really believe them, but maybe it turns out, 50 years from now, this is not the way that the molecules react, okay? We were wrong. That could happen. So we kind of always say proposed. Okay, here's step I. Step I is the first step. Ozone hits a nitrogen dioxide to create NO3 and O2. So that's an oxygen exchange, right? The ozone is giving up an oxygen to NO2. That's the slow step. That's the hard step, right? That one requires a fair amount of energy. So, and ozone in the atmosphere is always hitting into NO2, but most of them don't react. First of all, they have to find each other in the atmosphere. The atmosphere doesn't have large concentrations of either one of these things, right? This is not like oxygen, O2, and N2, which are prevalent in the atmosphere. These guys are far apart. They're in small concentrations, okay? So that's the slow step. That's the rate determining step. I'm telling you that to get this and this. Okay. Well, we can calculate the rate law for that. The rate law for step I should be the rate constant for step I times ozone to the first power times NO2 to the first power. Good. The second step is that NO3 that you just created, that intermediate, hits another NO2, and those 2 things combine. An NO3 and an NO2 get together, they make a nitrogen-nitrogen bond to make N2O5. So they're going to actually hit like this. You think of the NO3 and the NO2, right? They're going to combine to make N2O5. How cool is that, right? So that's what you make. And that's the final product. So you can remember, you can always go back and look at the steps in the reaction and get the overall reaction. So let's see what cancels out. NO3 is an intermediate. It cancels out. This and these 2 guys don't cancel out, right? So I have ozone plus 2 NO2s as reactants. Okay, this guy canceled out with that guy. So I have N2O5 and oxygen as the products. And look, those are the products. Okay. All right, so this kind of makes sense. The rate for the overall reaction has got to be the sum of the rates for the 2 steps. First I do this, then I do that. Okay, so let's go back to our grocery store thing. First I go there. It takes me 5 minutes to get there by car. I'm shopping for 1 hour. and then I come back. So that would be a 3-step reaction, 5 minutes plus 1 hour plus 5 minutes. Well, if the second steps, if those faster steps are so much faster, not an hour and 5 minutes, okay, which are, people, 5 minutes does matter to people. How about if one thing takes an hour and the other thing takes a second? Who the heck cares about the second? It's so much slower, okay? It takes so much less time that we can just ignore it. Well, that happens a lot in chemistry. If you have a first step that's very slow and the second step is 1,000 times faster, these two really love each other and want to react like crazy, okay? Because you're not breaking any bonds, you're just forming a new bond. You're taking two things that are unstable and making this nice stable thing at the end, right? Oh my God, it takes forever, it takes forever, it takes forever, it takes forever. Woof. It takes forever, it takes forever, it takes forever, it takes forever. Woof. Okay, who cares about the woof? It's so much faster that you can ignore it, okay? So if the second step is faster than the first step, just throw it out. The amount of time it takes doesn't matter. The rate is going to be equal to the rate law for the first step. So that's the first example. The first example is if the first step is slow and it's followed by any faster steps, it doesn't even matter. This one just has one faster step. But what would happen if the next one was fast and the next one was fast and the next one is fast? You can ignore them all. If the first one is slow and the ones that come subsequently are fast, ignore them all. So it's kind of like the rate for the first plus the second plus the third plus the fourth plus the fifth. Who cares about all that stuff? They're so much faster. Remember, it takes forever, it takes forever, it takes forever, it takes forever. Woof, woof, woof. They go so fast, those woofs. You can just leave them out. Okay, recap. First one, slow, then the rest of them are fast. The rate constant is just equal to, the rate is just the rate for the first step, okay? So K is just Ki, because the only one that counted, the overall rate, is the rate for the first step because we can ignore any subsequent steps. Okay, so that for our reaction, let me make this a little bigger. First one slow, everything else faster. The rate law is just equal to the rate of the first step, and you can use the coefficients because that first step is a molecular process, okay? It's an elementary process. This guy to the first power, this guy to the first power. The overall K is just equal to K for the first step. That's the only one that counted. We just ignored those other ones. Okay, let's read some notes and then we'll look at one more example that you're responsible for. So you're responsible for if the first one is slow and then the other ones are faster, and you're going to be responsible for one more. Okay, the overall rate law in any reaction must be consistent with the mechanism. That makes sense, right? So if you go back and do the experiments where you change the concentration of the overall materials and you see the reaction speed up or slow down, that has to be consistent. So if you did a series of experiments, you should find, right, a series of experiments with the overall reaction, and you adjusted the concentration of ozone and the concentration of NO2, you should find that it's first order in ozone and first order in NO2. Even though this is a 2, who cares? That when you double the concentration of NO2, the rate should go twice as fast, right? Whatever you do over here, you get the same relationship over here. That's first order. Same thing with ozone. Quadruple the concentration of ozone, it'll go 4 times faster, okay? Because this is to the first power and this is to the first power. And second, any steps after the slow step, the rate determining step, do not affect the rate of the reaction. They are not important to the rate law. Okay, last example. What about mechanisms with an initial fast equilibrium step? So you have the overall reaction. The first step is going to be a fast equilibrium step, meaning it can go in both directions and come to equilibrium. And then it has a slow step. And then maybe it has a bunch of fast steps, okay? In this case, I've got a fast equilibrium, right? That's the key, not just fast, but fast equilibrium. If I have a fast equilibrium, so it can go forward, the forward is K1, but these two things can very quickly turn around and go backwards, so they're at equilibrium all the time, right? There's so much, this equilibrium here is so much faster. Let me get this right. How's that? Okay, here's the overall reaction. Dinitrogen pentoxide breaks into 4 nitrogen dioxides plus oxygen. So different chemical reaction. Okay, this is a fast equilibrium step. So it can go to the right to decompose into NO2 and NO3, but the NO2 and NO3 can quickly come back to give you N2O5. Okay, so this is happening maybe 1,000 times faster than this dragging one. So that's I. Well, here's II. II is the NO2 gets together with an NO3 and does something different. So these two things don't hit and go back. They hit in a different way and make NO, NO2, and oxygen. This is slow. This takes forever. Okay? But you can't have that occur. You can't have these two things get together to go to those things if this first one doesn't give you a population of NO2 and NO3s. So we need the first thing to break down so that they can hit again in a different way, so that instead of combining, he extracts an oxygen from it to make NO, NO2, and kick out an oxygen. All right, so that's the slow one. That's the one that takes forever. Now, the last step isn't going to be important because we know any fast steps that happen after the slow step don't matter. Because it takes forever, poof. Okay? So, what do you do with that? NO3 gets together with NO under K3 for step 3 to make 2 NO2. So obviously, I'm not going to do it, but if you add up all of the steps, you better get back the overall reaction. You should get 4 NO2s. Here's 2. Here's 1. Here's the other one. So there's the 4 NO2s. Where's the oxygen? There's the oxygen. Here's 1 N2O5. Okay. I'm going to need another N2O5. Right? Because I got 2 up here. I got to get back the overall reaction. It's interesting. Here's 1. I don't see the second one. Let's go back for a second. Let's make sure everything else cancels out. So this guy could cancel out with this NO3, cancels out with this NO3. This NO cancels out with this NO. Then what I must be getting is, another N2O5 over here. Yeah, it's interesting. I don't see. I only have one of these guys over here. And, no, that would be 2. I need 2 times 2 is 4 to give you that. And that would give you 8, and 2 is 10. So this is correct. I got to think about that. It doesn't affect the rest of what we're going to do. Okay, but usually everything you get over here, you've got to get back over here when all the canceling goes on. Okay, all right. So this is a cool one. Any fast steps after the rate determining step don't affect the overall reaction. So step 3 is not a factor. Well, we already knew that. So I don't have to worry about this because it goes so quickly after that. So it's like forever. So this one goes super fast. So we can ignore the third step. So right now, we know, write the rate law for the slow step, and then take this fast equilibrium step, and let's see if we can plug in for any intermediates. That's going to be our rationale, so that we can get the overall chemical reaction, we can get the rate law for the overall reaction and eliminate any intermediates, because intermediates you should not have in the rate law. Right? They're too fleeting to measure. So you make it and then you use it up. So that's going to be our rationale write the rate law for the rate determining step. So for step 2, and I'll bring it back in a second, for step 2, it's K2, because it's step 2, times NO2 times NO3. So that's your first thing that you do. What are we trying to do? We're trying to get the rate law for a chemical reaction that you have the mechanism, and the mechanism is you have a fast equilibrium step before a slow step, and then it doesn't matter what happens after that, because we know we can ignore everything after that. Good, so we're ignoring everything after that. So step 1, I shouldn't say step 1, thing to do 1, write the rate law for the slow step. So I need, what is the rate law for this? The rate law for step 2 is K2 times NO2 to the first power times NO3 to the first power. And there it is. NO2 times NO3 to the first power. Okay? Now, substitute for any intermediates. Which of these two things is an intermediate? Because you can't have intermediates in there. Okay? Well, for step 2, this is the guy that's the intermediate, right? Because you created it in step 1, and then you're going to use it up in step 2. This is a reactant, so this is okay. This is not an intermediate. Okay? So we're going to substitute for NO3. Here, this guy is created, and then it's a product over here. Okay? So we're going to substitute in for NO3. All right, well, remember, what does it mean for something to come to equilibrium? The definition of equilibrium is when the rate of the forward reaction is equal to the rate of the back reaction. So let's write the rate for the forward reaction in step 1. That's rate I for the forward, right? So I'll go back, I don't have to rewrite it, I'll go back and show you. The first reaction, fast one, is going to be N2O5 to the first power times K1. Okay, there it is. The reverse reaction, rate I to the minus 1, right? Going backwards, is equal to K to the minus 1 times this guy to the first power and this guy to the first power. Why? Because now we're going backwards, right? Going backwards. Look at that bottom arrow. If it's a, this is a mechanism and these are elementary steps, going forward, this is going to be to the first power. Going backwards, this is going to be the first power. This is going to be the first power because these are reactants going backwards. So I have K to the minus 1 times NO2 times NO3. Good. Now, at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So these two things are equal to one another, right? At equilibrium, the rate of the forward reaction is equal to the back reaction. So equate them, make them equal to one another. Set this equal to that. Rate of the forward reaction is equal to the rate of the reverse. So I just take all this and make it equal to all this. I could just make these equal to one another. Okay, equal to one another. So if this is equal to this, that's what I have down here. Now, last step, solve for the intermediate. Get NO3 all by itself. Right, we weren't supposed to have NO3 in there because it's an intermediate. Right, back over here. When we got, when we got done for the first one, right, we'd almost be done because this is the slow step. Now we just have to substitute in for any intermediates so that we don't have any intermediates left. So that's what I'm substituting in. So all I need to do here is take this equation and solve it for the intermediate that's in the slow step rate. So that's NO3. So do the algebra. Leave this guy by itself. This and this come underneath. So I get the intermediate concentration, the equilibrium concentration of NO3 is equal to K1 times K to the minus 1 times NO2 N2O5 divided by NO2. Take this, and let's read this first. So this part I solved for NO3. Since step I is fast with respect to step II, the concentration of NO3 is given in the expression throughout the equation doesn't change. It's so fast, you're always at equilibrium. Okay? So this thing, fast, back and forth, fast, slow. So my reservoir of these two things never changes, because even when they react, this reaction occurs so slowly that it doesn't make a difference in the pile of them. So this concentration stays the same. The concentration of the intermediate stays the same throughout the reaction, because this is so much faster than the ones before. Okay, so you have something coming into equilibrium so quickly, and then you're grabbing them off the pile. This re-equilibrates instantly, 1,000 times faster than this reaction. So that means the concentration of N2O3 will always be given by that little equilibrium concentration that I just figured out. So that's what we do. We now know that the concentration of the intermediate NO3 is always going to be this, so we plug that back into our rate law. Okay, so I'm going to do that on a piece of paper because I should have given you a little bit more detail for that. Okay, so let me do that right here. Okay, so for step two was the slow one, right? So I'm going to go back now, and I'm going to take what I just learned, and I'm going to plug it in. Okay, so here's my NO3. I just learned that that's always K1 over K to the minus 1 times N2O5, all divided by NO2. Good? All right. Well, this is the slow step. The slow step is the driver, the one that matters. So go back and plug this in for NO3 into the slow step. Okay? Well, remember back here, here's the slow step. Right here. Right? Step II. So let me just rewrite that on this page. NO2 times NO3. I can't have NO3 because it's an intermediate. So this is going in there. So if I put that in there, I get the rate law for the slow step, the step that matters, the driving step, right? The rate for the overall equation is going to be related to the rate law for the slow step once I get rid of any intermediates. Leave this NO2 alone. Rewrite all it. Oops, sorry, I needed a K2 here. Okay, so I'll put that there. Okay, got to substitute in for that. I put in a K1, K minus 1. These are all lowercase. Times N2O5 all over NO2. Okay, gather up all of the K's together. K1 over K minus 1. These are just constants. Times KII. All of those together are going to make one constant. This and this cancel out, right? So the rate law for the overall equation, the only thing that matters is the concentration of N2O5 to the first power. This is the rate for step II, the slow step, the rate determining step, the step that matters. Okay, well, what would the rate law originally have been if I didn't know anything about the mechanism? Go back to the overall equation and use x's and y's. The overall equation says that it should be equal to, so this is the experimental one. This is the one that comes from the mechanism. The one I'm going to write here is the rate for the overall. If I'm only working with overall, all I can do is look at the overall equation and say it's equal to K overall times the concentration of any reactants to some power that I need to determine experimentally. Don't just take the 2 and put it up there, because this is an overall reaction. And what did we just figure out by looking at the mechanism? That this is not just x is to the first power. We figured out that x is to the first power. So this and this are exactly the same. K overall is K1 over K minus 1 times K2. This is just 3 constants that should be the same as your overall reaction. The constants for the individual steps put together like this will give you the overall constant. Okay? So the rate for the overall chemical reaction is equal to the rate of the slow step. If you have any fast steps after the slow step, you ignore them. If you have any equilibrium steps like we had in this problem before the slow step, what do you have to do? You have to go back and substitute in for that equilibrium what it's equal to based on the equilibrium equation. And that's how you're going to get the overall reaction from the mechanism. Okay? So if it's slow, then a bunch of fast, that's easy. You just take it for the slow. If it's fast equilibrium, slow, bunch of fasts, write it out for the slow step, then plug in any intermediates that you get by doing the algebra from the step before it, because the step before it is always at equilibrium. Okay, I don't want to over say it. I'll just leave it right at that. Okay, so here's the end of that section. Let me just make this smaller for you. Okay, and we will practice some more. So all those two things cancel out, and you get the rate law for step 2 was equal to those combination of rate constants times N2O5. Okay, this is what we just said. Here's theory. Here's experiment. Experiment is when we got this, how did we determine that this was to the first power? We did a bunch of different experiments where we varied the concentration of N2O5, and we saw that the rate doubled when we doubled the concentration. If we made the concentration 10 times bigger, the rate would be 10 times bigger. That's first order. When whatever you do over here, you get the same thing out over here. Okay? These two things have to match up. The mechanism has to match the experiment. And the overall rate constant that you would have gotten from the experiment is just the sum of these rate constants, right? Let's say you find out like a number is equal to 10, right? Because you do the experiment. Well, you can get 10 a lot of different ways. Here's the way that we got 10. 5 times 2 over 1, okay? That's equal to 10. So if you just know 10, you don't know how you get it, but it has to be that you put together the parts, you're going to get back the same number. Okay, so that ends that discussion. The last thing we're going to talk about is we're going to do qualitatively, completely qualitatively, and that is this idea of if you break down any elementary step, what's actually happening? Okay, so this is called the idea of transition state theory. So you're basically going to follow the step in the mechanism, the elementary step, and ask yourself, what does it look like when the bonds are halfway broken, right? What does it look like at the top of the mountain, at the highest point, right? When everything is all broken, you're a long way, you don't really have any, you're not going to get any energy back yet, right? That's going to be the top of the mountain. So we know what this number is called here. Oops, sorry, start from here. The difference between the starting point and the highest point is the energy of activation. So our chemical reaction that we're going to use as a example is A bound to B, right? So this is one substance, A is bound to B, smashes into C. So I'm telling you this is an elementary process, okay? Smashes into C. So on the way up this hill, what's happening? Well, A and B are breaking, right? They have to break. And C must have attacked the B side because it winds up with B. So here's A and B. C comes in, smashes into B from this side. This bond starts to form. The BC bond starts to form at the same time that the AB bond starts to break. How do I know that? Because I'm telling you this is an elementary step. It didn't happen in 2 steps. Right? So this is an elementary step. In an elementary step, this is called a concerted reaction. It happens in concert. The AB bond starts to break. So how do I draw that? I draw that with a dotted line. Right? It goes from a nice, beautiful single bond to a bond that's stretching and breaking. The same time that the AB bond is breaking, the BC bond is forming. So this is bond formation. This is bond breaking. So picture that. Why does that take energy? because I got to break AB. That's hard. Okay? Then I get to the top of the mountain here, and I come back down. Now, A goes off, and I form this very strong BC bond. And this turns out to be slightly less stable than this. How do I know that? Because it's higher up in energy. Okay? So the energetics of it is that this is an endothermic reaction. I went uphill, right? This is potential energy, or H, enthalpy. So what's delta H? Delta H is H2 minus H1. It's just this little difference here. What's the energy of activation? The difference between the starting point and the highest point. That's energy of activation. Okay? So the energy of activation is the amount of energy to create this intermediate. Okay? So how are we going to describe, excuse me, that's not an intermediate, that's a bad word to say, to create this transition state. Transition state is not even fleeting. Okay? It's just a pass through. You don't even hang out for a little while. An intermediate, if I had to show you an intermediate on a potential energy diagram, it would look like this. It would be like a little resting point. Okay? This would be a two-step reaction. See? That's an intermediate. I go up in step one, I go to here, create this intermediate, lasts for just a few seconds, then I go up another hill and I get down to the products. This would be a two-step reaction from here and then from here to here. So this would be step one, and this would be step two. And that little hole in there is an intermediate. So step one has a transition state. I've got to break the old bonds and create the new bonds. This is the transition state. I think I make a cool thing that looks like that for step I. And this top of this little mountain over here would be the transition state for step II. Okay, so don't confuse intermediates that are down in a little hole here. You can rest up, right? It's like hiking. You're never supposed to hike above tree line, right? So you go hiking, you stay above tree line, you hike on the top of the mountain, across the mountains, and then when it comes to sleeping at night, you're not going to go all the way back down. You're going to camp out just under the trees here where it's safer and you won't be hit by lightning. Okay? And you wake up in the morning, you go back up, and you climb that mountain and over. So you stay up, but you don't stay in a dangerous area. So these things are called the transition state between the reactants and the products. This is the first step, and this is the second step. They're broken up. So I could do, if this was A and getting together with B and make the intermediate C, step one would be A plus B goes to make C. And step two, C turns around and goes and makes D. So the overall reaction, C is an intermediate, I use it up. The overall reaction would be A plus B makes D. That's the overall reaction. This is A plus B, and this is D over here. Okay? So C is what I have at the intermediate. I got A plus B, I make C. So that's a two-step reaction. So I could make a transition state for each of those. What would be happening here? A and B would be getting together on the way up the hill and then creating C over here. Then C, I'd have to stretch those bonds and break those bonds before it turned around and made D. So the top of the mountain has a special name. Those are called transition states. So let me read these two things to you and I'll stop right there. Here's my example. Okay, this is in one-step reaction. Here, the one I just did was a two-step reaction with an intermediate. So let's talk about the one-step reaction. So transition state theory explains the reactions resulting from the collisions of two molecules in terms of an activated complex. The activated complex is this thing over here. The top of the diagram, we call that the transition state. It's like taking a snapshot right in the middle of the reaction. Okay? Not a stable place. It's just a super fast photography, right? Like when you see an apple with a bullet going through it, it's super fast photography at the very apex when the things are the worst, right? Why are you so high in energy? Because you have put all the energy in to break A and B, and you haven't gotten much back from forming C yet. The forming C will come on the way back down, okay? The activated complex or transition state, which gets this little symbol, is an unstable group of atoms that can break up to form the products, the halfway point of an elementary process, okay? So if this is an elementary process, that's the halfway point, okay? And we're plotting enthalpy or potential energy versus the reaction coordinate. This is basically time as you move from left to right. This is before they react, this is after they react. So you can always have a halfway point where the old bonds are breaking and the new bonds are formed. It happens at the top of the energy of activation. Okay, that's long enough. That's an hour and 10 minutes. We are done with chapter 14. Have a great day, guys.